Okay, today we're going to talk about the magnetic field of the sun. In the last lecture, we talked about uh, how the sun generates energy, and it generates the energy in the core by nuclear fusion, and it generates gamma rays and neutrinos in the process. And by the way, here on Earth, sometimes they try to measure solar neutrinos. We do have reactions here which can produce neutrinos, and sometimes they go very deep in mines to try to measure this solar neutrino. And then we talked about these sunspots, and we said that the sunspots have lower temperature than the average temperature of the surface of the sun, and that's why they look darker in comparison to the surface of the sun. And the magnetic field, when you have sunspots, are 1,000 times stronger than what's around it, and that gave a clue that this magnetic field holds the convective material for longer time, so it becomes cooler than the rest. But they're hot. They're about 4,240 Kelvin. And we stopped here where we wanted to basically look at the magnetic field of the Earth, of the sun. So now, if we look here at the sun, we have something that we call differential rotation. And in the differential rotation, because the sun is made of gases, and the sun is rotating as well. So if you take a point, or you look at these points that I have here on the surface of the sun, and then as the sun is rotating, and in the middle here we have the equator, these basically points have basically move a little bit further, meaning they are basically having higher speeds. So this is what we call differential rotation here. So when we look at the sun, we say these basically may take about 25 days. This probably will take 35 days. So it takes a longer time, shorter distance, so it's basically have lower speed. And that's why we say here that we have differential rotation. So that's one thing that we have to keep in mind here. Now, the second thing, as I told you, that in the sun we have a plasma, and this plasma is ionized ions and atoms, and due to this, they are moving, and if they're moving, they constitute currents. And when you have an electrical current, you basically produce magnetic fields. So due to this differential rotation and the motion of these plasma, then you can produce magnetic fields. So what is this structure of the magnetic field of the sun? Is it as static as we see for permanent magnet? No, it varies. So now, when we look at sunspots, for example, you always see that the magnetic field that come out of the sun, they loop back. And you all know about magnets, they always, or magnetic field lines, they go from north to south. So as you can see here, the magnetic field loops and come back. It loops and then comes back. It's looping and coming back, and that's basically an evidence of magnetic field lines. Now, when you look at sunspots, you always find them that they are not alone there. There are regions where the magnetic field basically will loop out and then it come back. And that's why we said in the last lecture that these magnetic field lines are anchored in the photosphere of the sun. And the magnetic field, when you have a sunspot, seems to be stronger. So how would this, and we told you that the magnetic field also, because the sunspots, they go through a maxima every 11 years, and we said this has to do with the reversal of the polarity of the magnetic field. So how the sun generates this magnetic field and how it basically gives this 11-year reversal from north to south, and then it goes back in another 11 years. So we said the total cycle for polarity is 22 years. So if we just look at the cartoon that we have here, which is, you have here just one magnetic field lines. So you have moving plasma, it produces magnetic field, and you know that magnetic field lines will go from north to south. So if we have just one magnetic field line, and the sun has a differential rotation that I already told you. So what will happen to this line? It's going to be deformed. So it's not going to contain, it's not static like what we have for permanent magnets. So it's going to change its shape as this differential motion. And as the sun is rotating, and I think I showed you in the last lecture where the sun is basically rotating, it was in some period in 2011. So the sun is rotating around this axis. Now this line will be basically start wrapping itself around in such a way that these will come close as you go around. This wrapping will become close to each other. Maybe at some point they can twist around each other. And the strength of the magnetic field is proportional to the number of lines. So in some places, when you have more magnetic field lines twisted on each other, then that will give you the strength of the, that will give you more magnetic field strength in this region because you have more magnetic field lines. And they loop out and they loop back. If you're wearing a shirt and you know that it's the fabric that the shirt is netted from, now sometimes you may actually have something that sticks out and then comes back. You either cut it or you try to stretch the shirt to bring it back into the fabric of your shirt. So that's the idea here. So just to show it in blow up, if you can basically look at a magnetic field line, and we're just looking at one here to show you the effect of the differential rotation on it. Now, as you the sun rotates, and we have differential rotation, so at the equator, things are a little bit faster, so it will be deformed in a shape like this. Then as it comes around, it will be wrapped around more, as if you're taking, you know, these wall string that you can wrap around in a ball, and then you can net sweaters and things like that from it. You can look at it in a similar way. And when they actually start rotating and rotating, these lines are getting closer and closer. So sometimes, if you look here, they may twist around one another. And they stick out and then they come back. And that's basically when more magnetic field lines, that means you have more strength of the magnetic field, and more strength of magnetic field, that means the material that it's there, the magnetic field will inhibit its motion, so it will be held for longer time. You get lower temperatures. Of course, some material can shoot out and come on this magnetic field lines, and we showed this is the evidence of where we see these magnetic field lines. But when we look at sunspots, usually you find them, they come in pairs, where a magnetic field line will leave and then it has to come back. We see this in something that we call prominences, and these are looped gas that is ejected from the photosphere. Of course, it's not from, it's below, it's very hot. So it will go up and then it comes back, and that basically gives us the evidence of this magnetic field lines. It's a material that it finds itself trapped on these magnetic field lines. In some cases, the temperature there is about 60 to 80,000 kilogram. Of course, when you go higher in the corona, it's about 1 million degrees. Just to give you an idea here, that's the size of our Earth, and that's basically the shape of something that's looming out of the sun. And of course, a material is trapped on these magnetic field lines. That's another view here. We take it in the ultraviolet, and in the ultraviolet you can basically see the granulation due to convection, and in this case this is where the Earth is in size, and this is what we call a solar flares. So when things break and you get this solar break, and that can basically send in solar winds. And these winds, as we discussed earlier, they go through the whole solar system. When they come to the Earth, as in chapter number 7, it has a liquid core, and this liquid core is responsible for creating a magnetic field, and this magnetic field is kind of a shield from solar winds to the Earth. So these solar winds, when they come, the magnetic field of the Earth does not basically stop them, it just only deflects them away. But some of them, they leak from the North Pole and the South Pole, and these basically cause what's known as the Northern Lights, which is called Aurora Borealis. Now, these are, just to show you here, the shapes of the magnetic fields, but in the Earth, that's exactly what we see. So sometimes those who look at space weather, and they look at the sun surface, and they look at the sound waves that are produced by these solar flares, which of course they may eject solar winds. We call them here coronal mass ejections because they come from the corona, and sometimes they refer to as CMEs. It's the plural, okay, will become coronal mass ejection, so CME, but you may actually hear sometimes they say CMEs. Okay. And these, you can see here, that's when you block the sun, you can see these. And this is what causes these northern lights that we see in the North Pole or in the South Pole. That's the small amount that leaks from the North Pole and in the South Pole. These solar winds, when they come and they see, they hit the magnetic field of the Earth, they're deflected, but some are basically trapped in the Van Allen belt. And basically, when you know that all those magnetic field lines, they start from north and they terminate at the south. So you may actually have the magnetic field this way. So that's where they can leak, okay, from the south and the north, and they interact with the gases in the atmosphere of the Earth, and they cause this wonderful effect. If we do not have this magnetic field, then probably they are very energetic. They can burn the atmosphere of the Earth, and of course, if they burn the atmosphere of the Earth, then finally you don't have the atmosphere, you don't have the greenhouse effect, you cannot achieve the comfortable temperature for liquid water here, and that's very important for life. So even we're lucky as well that we have the structure that we have in the Earth, which is the core. It has a solid core and then the liquid core. We're happy that we have that hot iron at 6,000 degrees in the core of the Earth, which basically is responsible for the generation of the magnetic field. And then you have the mantle, and on top of the mantle, you have the crust. So it is a shield for us from the solar winds. Now, this is when you take an image of the X-ray. So the X-rays have small wavelengths, high frequencies. So you're using higher energy here, and you look at these wavelengths, what you can see, and you see something that we call here coronal holes. And these coronal holes, basically, when you have open line fields, and that's the origin of the solar winds that comes toward the Earth. So that's an example here where you see coronal holes, and that can basically send in these solar winds that are harmful to our atmosphere. And I told you in first lecture that some may argue that if the sun is continuously losing these gases or ionized gases, then eventually it will lose its mass. And I told you this basically very small compared to the mass, is 1/10 raised to the power minus 14. And in chapter number 9, we'll talk about the age of the sun, and we'll say that the sun can live for about 10 billion years. And in chapter number 6, we said that the age of the solar system is about 4.6 billion years, roughly 5 billion years. So the sun still has 5 billion years to go. Now, the last thing that we want to talk about here, which we call the solar constant. And the solar constant is basically the energy we receive from the sun, which is essential for all life on Earth. Remember in chapter number 5, when we talked about the electromagnetic waves. So the sun now is producing all of these electromagnetic waves. And these electromagnetic waves go through the whole solar system, so it comes to our Earth. Now, the atmosphere of the Earth blocks the X-rays, the gamma rays, big part of the ultraviolet, big part of the infrared, and basically you get the visible light and you get the radio waves here. And this energy that we receive from the sun is essential. With the atmosphere of the Earth, it can have the greenhouse effect that basically give us the comfortable temperatures that we have here. Now, there is a problem with the global warming. It's because we are putting more gases, CO2, in the atmosphere, which can trap more heat. And of course, if we trap more heat, that will raise the average temperature of the Earth and could melt the polar caps, north and south, and that will give rise to the oceans and the water bodies on the surface of the Earth, and that, of course, will lose more land. So we need the greenhouse effect, but we have to keep that in balance. Now, the amount of energy that we receive from the sun that reaches the surface of the Earth, we call it solar constant, and that's equal about 1,360 joules per meter squared per second, and we call that flux. It's continuously coming. So if we take 1 meter squared, an area of 1 meter squared, this area of 1 meter squared, it receives about 1 1,360 joules every second. So that's expressed as the energy flux, and sometimes we call that the solar constant. And that's what the Earth is receiving from the sun. Now, if we can convert all of that into energy, then it's sufficient for us here to have the energy that we need. But of course, we have to find ways to convert this energy. Now, this energy, of course, is probably causes changes in temperature and pressures, and that's why we have winds. Now, you may actually have wind turbine where you, in their motion, can produce, like the effect of the dams, it can produce electrical energy. Or we have the photovoltaic cells. And the photovoltaic cells, they will work on light because what we receive here is visible light. So we have to design them on converting this visible light into electrical energy. And I told you about the photoelectric effect. So there are some materials that absorb light and produce electricity. And that's how we design photovoltaic cells. We call them solar cells because they rely on this renewable light that continually comes from the sun. And that's why the sun is very important to our planet here, Earth. So this is basically how the sun is operating, and it's important to us. And if we learn how the sun is operating, then we basically can say something about other stars are far away, and we discussed about the exoplanet, and I told you that the number now is about 4,401 exoplanet confirmed. That means that the presence of planets orbiting other stars is common. Do they have conditions where we call habitable zone? That means in the habitable zone from their star, it doesn't have the same, it doesn't have, stars are having different sizes than the sun. So how far the planet is from the sun to be in that comfortable habitable zone. So this is something that scientists are trying to investigate now. What happens if we have to move to this? This is basically now the sun. Now we actually we can summarize the whole chapter, but we already talked about these points in chapter number 1 when we talked about the atmosphere of the sun, and we talked about the 3 layers. There is one point here that probably I will try to say, which we'll call the edge or limb of the solar disks is dimmer than the center. Now, when you have a sphere like the sun, now in the edges here, when you go around, of course, they will be further from you. And further from you, that means sometimes we call this limb darking. And limb, you know what a limb is, okay? Your hands and things like that. So they're further away from the center. So in the center, because of this huge sphere, so what you receive from the edges will be less. Then we use filterograms to look at the chromosphere, and we talked about the corona, and then we talked about the helioseismology. And in the last lecture, we talked about the nuclear fusion and how the sun is basically producing its energy, and we talked about its proton-proton chain because it only concerned with the nucleus. The protons have no role into this. The electrons have no role into this. We're only concentrating on the protons inside the nucleus, and in the process you're producing gamma rays and energies as well later on that comes from the different surfaces. And then we talked in the last lecture about sunspots, and we said these are basically coming from the solar activity. and we said they vary from maximum to maximum every 11 years, and that has to do with the reversal of the magnetic polarity. And we talked about the Mandarin butterfly, and we talked about the Mandarin minimum as well. And today we basically capped up with the structure of the magnetic field of the sun, and then the solar constant, which is basically the energy that we receive from the sun. Any questions on these? Any questions on these? Is this clear? Any questions that? So that's basically how the sun works. Now there are the Parker probe that is orbiting the sun and trying to look at the effects of the sun. There are basically other orbits now. They get closer and they can look at the structure of the magnetic field that we talked about. But the magnetic field is something that is dynamic, is moving, unlike what you see for permanent magnets here. I don't want you to think that it's like a permanent magnet. So it's not that easy to look at the structure of the magnetic field of the sun. So from here, they usually model this. Now, the next part that we're going, or the last thing that we want to do here, is we're going to look at the review questions that we have for chapter 8. And as usual, I always say that these review questions is we give you the answers, but you have to answer. You have to understand why these answers is the right way. So the first question here: granulation is caused by, and they give you options here: rising gas below the photosphere. Actually, it's the hot gas rising and the cooler gas sinking. Now, in some regions of the corona, the magnetic field does not loop back to the sun, and the gas escapes and embedded. The regions are called coronal holes and are believed to be the source of the solar wind. Three, most of the light we see coming from the sun originates in the photosphere. 4, modern astronomers suspect that the corona is heated by the solar magnetic field. That's why the corona is very hot. It has to do with the magnetic field of the sun. 5, the centers of the granulars are hot material rising to the photosphere from below. And remember, we said the center is hot, and then the edges are cooler. And that's how you get these granulars, or we call them granulation, and this is in the convective zone. The solar wind is the hot gas that are moving extension of the sun's corona. And remember, we told you the sun corona extends to many radii of the sun. So it's very far from the sun. And when things break loose, they come to the whole solar system as solar winds. Limb darkening occurs because photons we receive from the edge of the solar disk are emitted further from the base of the photosphere than the photons we receive from the center of the solar disk. The sun is a huge sphere. So what we receive from the center will come faster than what we receive from the edges, and this is known as limb darkening. High temperatures are required to get H nuclei to fuse because they repel one another because of their positive charge. Remember, in nuclear fusion, it is the nucleus of each hydrogen atom that we want to fuse together. And inside the nucleus in hydrogen, you have a proton. Proton is positively charged, and positive, they repel, and that's called Coulomb repulsion or electrostatic repulsion, and you need a temperature more than 10 million degrees to overcome this in order to fuse the hydrogen nuclei, and that's why we say here they repel. Because of what? Because of their positive charge or because of the electrostatic repulsion. 9, most of the energy emitted by the sun is generated in the core. It comes from the core, but it goes through the different layers, and it will give you all of these different energies that we receive, either in terms of gamma rays, X-rays, ultraviolet, UV. These are all processes when ionizing the gas in the way. 10, the energy generated by the sun is released by the fusion of hydrogen nuclei to helium. Now, I told you should not be confused between fusion and fission. So I don't want you to say, well, it's maybe C. No, actually, the right answer here is A, fusion. And here we have fusion is promoted in the core of the sun by high temperature and high density. So you have in the core of the sun, the temperatures are about 15 million degrees, and that can promote the fusion. And of course, you need high density of the gas to basically do that. And I told you, we need about 10 raised to the power 38 reactions, which is about 5 million tons of mass that's converted into energy. 12, sunspots are dark because strong magnetic field inhibits the current of hot gas rising from below. You know about the convective process, where the hot gas is rising and the cool gas is sinking. So if something inhibits this motion, it's going to stay for longer time, and it becomes what? It becomes cooler. 13 here, the intensity of a sunspot is found to be 3 times smaller than the intensity emitted by the solar surface. The temperature of the solar surface is about 5,800 Kelvin. What is the approximate temperature of the sunspot? Well, the closest one here is 4,400 Kelvin. I did not do that when we look at the intensity and we relate that to temperature. It's in this equation, and you can calculate that, but we know that the surface temperature of the sun is about 5,800 Kelvin, and we know that the sunspot is lower in temperature with about 4,240 Kelvin, which is very close to this. But this can come out of the equation, but we're not going to deal with that. 14, the solar constant is a measure of the amount of solar energy reaching the Earth. That's what the solar constant is. 15, sunspot cycles affect the latitude at which sunspots are visible at a given time. Remember, Mandarin basically did that. The number of sunspots that are visible at a given time. The rotation is not a factor, but the magnetic polarity of the sunspot at a given time. And we said they go through maximum, minimum because of the polarity reversal. Now, 16, the sun's magnetic field is evident in the loop shape of the solar prominences. That's what gave evidence for the magnetic field of the sun. Spicules, the spikes that we see in the chromosphere, are visible in filterograms of the solar chromosphere. The most recent sunspot maxima occurred in 2012. The one before that, it was in 2001. When is the next maximum expected? Well, you add 11 years to that, because we said every 11 years. So you add 11 to 2012, and it will give you 2023. A solar flare is believed to occur when energy stored in a twisted in the solar magnetic field above sunspot is suddenly released. That's when you have a solar flare. Now, just to give you an idea of how powerful these flares are, the United States consumed 2.5 times 10 to the 19 joules of energy each year. A typical solar flare releases 5 times 10 to the 24 joules of energy. How many years could we run the United States on the energy released by this solar flare if all of the released energy could be used? So you have about 5 times 10 to the 24 joules released by one flare. And if you divide by the energy needed for United States for 1 year, so you have 5 times 10 to the 24 divided by 2.5 times 10 to the 19 joules, it will give you about 2 times 10 to the 5, because 5 divided by 2.5, it will give you 2, 24, and you have 19 below. That means you have 24 zeros on the top and then 19 zeros in the bottom. So the 19 zeros will cancel 19 from the top and you get only 5 zeros. That's why you get 200,000 years. Just to tell you how powerful is one of these flares. But of course, we cannot do that. I mean, we cannot convert that energy. It's not that easy. We just have to rely on the energy constant that we receive here. 21, what is the explanation for pattern of a granulation seen on the visible surface of the sun? The granules are tops of hot gas that have risen from the sun's convective zone. So you have gas that comes in, hot gas rising from the middle, and of course cooler gas sink on the edges, and that's how we get the granules. 22, the gas motions within granules on the solar surface are upward in the bright cell centers and downward on the dark edges. That's why it's cooler on the dark edges and of course brighter in the center because it's what it is hotter. 23, what are the 3 layers of the sun's atmosphere in order of increasing distance from the surface? Photosphere, chromosphere, and then corona. 24, the rotation of the sun is fastest as the equator, slower at mid-latitudes, and slowest near the poles, and we call that differential rotation. Why the temperature at the region of sunspot cooler than the photosphere? We said that the surface temperature of the sun is 5,800 Kelvin. In a sunspot, it's about 4,240 Kelvin. Well, the reason for that, powerful magnetic fields inhibit the convective flow of the gases of the photosphere, allowing them to cool for longer than would normally be permitted. And that's why they will have a cooler temperature. And of course, in contrast to the surface of the sun, we see these sunspots as darker in comparison to the rest of the surface of the sun. So these are basically the review questions that we have here for chapter number 8. Is this clear? Any questions on these? Now the idea here is to understand why do we have these right answers. Of course, there are other, we can talk about the proton-proton chain reaction. We need temperature greater than 10 million degrees for the fusion of hydrogen. So these things also you have to keep in mind as well. Any questions on these? Any questions? Any questions? Is this clear? Good.